A power series is a special series of the form shown on the screen here. I have a coefficient an, I have a variable x, and I have a constant c. And the idea is that you're adding up powers of the quantity in the parentheses, x minus c. The c is a constant, and it's called the center of the power series. These are called the coefficients. And you should think of a power series as really defining a function, f, of x. Now, it may not be defined for all x. It only is defined where x results in a convergent series. So, caution, usually only defined for some x. In fact, the way the power series look in terms of convergence is that you've got your center here, and there is some radius r, about which your series converges in here. Maybe I'll do that in green. Converges. Series converges, and so the function is defined. And outside of the radius, the series diverges. Outside diverges. So the function is not defined there. And at the endpoints, well, you got to check. It may or may not converge or diverge. So these endpoints may converge or not. You need to check. Okay, this r, capital R, is called the radius of convergence. Of convergence. Okay, and you might ask, well, how do I find the radius of convergence? Well, the general way that you find the radius of convergence is the ratio test. It's everyone's favorite series convergence test. So you find the radius of convergence using the ratio test. The caution here is the final result looks a little similar, but it's different. To the usual ratio test. So be careful. Okay, so let's try it. Let me show you what that looks like. So the ratio test says I'm going to take the limit as n goes to infinity of the next term divided by the current term. And take this in absolute values. Okay, and the ratio test has you compute this quantity and examine it. When it's less than 1, you got convergence. When it's greater than 1, you don't. And if it's equal to 1, you got to go fish, figure it out. Okay, well, looking at this expression, I can simplify it right off. Because in particular, I've got n plus 1 factors of x minus c in the numerator and n of them in the denominator. So most of them cancel out. I just get one copy, one factor, and x minus c. And you will notice as far as the limit is concerned, that's a limit of n, so that really does not actually matter. I can factor out the x minus c. And in so doing, if we have convergence, at x, we'll likely have that this limit is equal to 1. So that says x minus c, or rather, not equal to 1, my bad, it's less than 1. So this is 1 over limit an plus 1 over an. These are n to infinities. And this is where I say be careful, because this is the opposite order. Even though it looks like the usual ratio test, it's not, because the an's plus 1's are flipped. This is the radius of convergence. Okay, so that's the main idea. And so you can use this formula to figure out what the radius of convergence for any power series is just by looking at the coefficients. So what this means is, in particular, the coefficients of a power series, not the center, determines the radius of convergence. All right, with that in mind, let's do a quick example. Let's do the following one, where we just have all the coefficients are 1. This power series, all the coefficients are 1. Right away you can see by that formula the radius of convergence is 1. Okay, let's do a little fancier example. So this fancier example is a series that defines a function called the 0th order Bessel function. It's a favorite function of mine. It looks kind of intimidating, but here's the thing. Power series are really handy for defining crazy functions. So this is the 0th order Bessel function, and Bessel functions show up quite a bit in physics and in wave propagation, which is why I kind of think they're cool. But the short answer is, think of it this way. Power series are useful for defining functions. And they turn out to be really handy if you want to solve differential equations as well. You could get out solutions in terms of power series often a lot easier than you can any other way. All right, now, all of that aside, let's find the radius of convergence of this. Let's find it. Well, the thing to do here is to realize that we got some coefficients involved here that are kind of crazy, and you can see that it's alternating. There's the minus 1 to the n there. There's got some denominator action. It's got some factorials and powers, and oh my goodness. You could just go ahead and use that formula for the radius of convergence, but honestly, I usually just find the ratio test is the way to go. So let's do that. Let's just use the regular ratio test. So if we do that, we're going to have minus 1 to the n plus 1, x to the 2 n plus 1, over 2 to the 2 n plus 1, n plus 1 factorial squared, over all of this. Okay, it looks like a big disaster, but it's not too bad. One thing to realize is the minus 1's have no bearing at all because they are inside the absolute values. The other is I could write this as a single fraction. So I've got an x to the 2n x squared. I've got an x to the 2n down here. In the denominator, I have 2 to the 2n times 2 squared. I've got an n plus 1 factorial squared. In the numerator, on the other hand, I've got a 2 to the 2n. And I've got an n factorial squared. Okay, time for some algebra. You can see a lot of things cancel. I've got an x squared n factorial squared over down below I've got, let's see, the 2 to the n's, most of them are still there. I got a 4 and n plus 1 factorial squared. Okay, now what about those factorials? Those are kind of a problem. But ratios of factorials should not scare you, because this is really just n times n minus 1 times all the way down to 1, and that whole quantity is squared. So that square propagates to each factor. Same kind of thing here, n plus 1 squared times n squared times n minus 1 squared all the way down to 1 squared. Okay, now you can see a whole bunch of stuff cancels out. Wow, okay. Now, after all of that, notice the x and the 4 are constants. This greatly simplifies, doesn't it? Okay, now that limit, what about that limit? As n goes to infinity, that limit goes to 0. So the whole thing goes to 0. What? The whole thing goes to 0. That means it doesn't even depend on the x, does it? So actually is what happens when you have an infinite radius of convergence. Which, in other words, means this series converges regardless of x. In fact, the Bessel function that we've got defined here, this guy, this 0th order Bessel function, is actually defined for all, not only all real values x, is actually defined for all complex x. So this is a pretty nicely defined function. It's what we might call an analytic function. As I said, crops up everywhere, and power series are a great way to define functions. And so it's good to get comfortable with them.